Good morning, everyone. So let me check everyone in. Um, Before we really get going a lot, I'll make this on. Yeah. Um, a few things to remember. There is a homework assignment that's due today by midnight. So you have most of the day to work on it. If you have any questions about it, still let me know. Um, let's see. Also, from Wednesday, we didn't have class, but I did ask that you go check out some of the videos from the Piedmont Symposium supporting your fellow students. If you didn't go do that, um, the videos are still up. You maybe missed the live version, but there are still recorded versions. And you can go watch the videos and write some brief summaries um, about those. And I guess in general, I would say if you missed any homework assignments, I will still take those late. So you can go back and complete those assignments and get some of the points back because some points is uh, definitely better than no points. Um, Yeah. Also, as we're getting close to the end of the semester, which is kind of strange because time just doesn't seem real anymore. Um, there is the final presentation that I made an announcement about. There's a on Canvas a written out description, and I would ask that by next Friday, um, you get in contact with me and have a discussion about exactly what your presentation is going to be about. Just so I know that you are thinking about it a little bit and you aren't trying to throw it together last minute, but also because you might not be sure what you're going to talk about. If you have an idea already, that's really great. If you found something interesting that has a little math in it and you'd like to learn a little bit more about it and get some points while you're at it, that's great. But if you aren't sure, I'd be happy to talk with you about some potential ideas. I wrote out a list in the announcement on Canvas, but a lot of the things in that list are pretty broad. Like something in there is history of mathematics. Well, your presentation is not going to be about the history of all of mathematics, but I can maybe suggest a particularly interesting person or story or idea to focus on, and then you can look up a little bit about that. So start thinking about that. If you have an idea you want to run by me, send me an email and we can do a little back and forth while you nail down exactly what your presentation is going to be about. Okay. Then let's talk about some stuff. So a lot of today, I think, is going to be um, looking at some pictures. I'm looking at some graphs because last time um, we started talking about maybe a little, in a more real sense, what these models are going to be, which is you're given some data points and maybe you can't find a function that hits them exactly. We had spent some time saying if you have 2 points, you make a line go through them. If you have 3 points, they might not all be on a line, but they might look like they're pretty close to a line. And so how do you deal with modeling when you have a situation where your data is a little more complicated? Yeah, so I'm not going to go into slideshow mode because I'm going to be jumping around here. Okay, so we've been, is this the right one? Okay, so that slide we talked about. Here's the sort of introductory slide. So for a few classes, we had this example. You're talking about numbers of trees and you're assuming they're growing linearly. And in this picture, what this prompt says is, you know that you have this point and you have this point, and if you try to find the line that goes through them, you can do that, and the equation of this line is 75x minus 250. Okay, so you do that by taking 2 points to find the slope using the slope formula. Given that number, which is 75, use that and one of these points to put it into point slope form, and then simplify it into this slope intercept form. But the more realistic situation is that we have other data points which don't fit this line. So this line doesn't exactly reproduce these other points. This point 11,580 and this point 15,888 are pretty close. It does exactly reproduce 12,650, but it's off quite a bit at 13,623. So a common question is, we have a quantity and we have a reason for believing it's growing linearly, but a line doesn't exactly match. But in this case, you might still want to say, I want to model this with a linear function. It might not be this one, but you would like a line which closely reproduces these points. And a way we can do this, and we'll see some more examples of this kind of thing using Excel, or really any spreadsheet software, whether it's Excel or Pages, I guess is the Mac one, or anything else for free. They come equipped with making graphs and then making trend lines. So what we did, or what Excel did for me in this case, is we have these same 6 points. And the line that it comes up with, the line that it makes to try to fit this data, doesn't actually go through any of them. Which you might think, okay, that's not great. But the reason why it doesn't is through some mathematical calculation. The idea is that if we make the line lower than these 5 points just a little bit, we can make it a little closer to this point. So rather than it being really good for these 5 points, and the picture we had on the last slide, it was perfect for 3 of them, but then close for 2 others, but then pretty bad for this one, we make it off by a little bit for these 5, but we make it not as bad for this point right here. And besides just drawing this line, Excel produces this formula, which is pretty close to 75x minus 250, which is good because both of those lines fairly closely approximated our data points, but this one is a little bit below them, so it is closer to this outlier low point here. What Excel also does is it produces this number r squared, which is essentially a measure of how good the line fits the data. with r squared ranging from 0 to 1, where 1 means it perfectly matches your data, and 0 means, in some sense, it doesn't match your data at all. So I haven't checked under the hood to see exactly what Excel does, but a common way of doing this, of coming up with this line, and we won't go through this process. If you took a stats class, you might see some computations where this happens. But one way of arriving at these approximating lines, sometimes called trend lines, that's the word that shows up in Excel at least, or the line of best fit, is what's called the least squares approximation. The square bit comes in if you were trying to do some higher dimensional stuff, so you can kind of ignore that, but the basic idea is that you have some number of points, which looks kind of like it's going up in a line. And so what you do is there's a kind of algorithm for figuring out what is the line that you can draw, which says when you draw that line, look at the distance from your line up to each data point. So you have these red points first, you draw this blue line, then you look at these green lines going from the line up to your point. And you would like to come up with a line that makes it so when you add these green lengths up, it's as small as possible. So that's one measure of how you can test how well a line you draw fits some data. Say, okay, see for each input here. So at 1, you can see the value of your data point at 1 and the value of the function at 1 and see how far it's off. And 2, you have the value of the data point, the data of the function, your model, and see how far they're off. But you don't just want to make one of these distances small. You somehow want to make all of them small. And so the way is add them all up. And so what is happening here is that if we instead drew maybe this line, right here. This line is really good for these points, but it's not very good for this outlying low point here. So the point of this blue dotted line is to say, if we move it down a little bit, we're not as good for these points, but we make it up by being a lot closer to this point. And so there's a balance you're trying to strike between if you make your line a little worse for a few points, you might make it better for some other points. So there's a real method to this that we won't go into, but there are ways of saying, given some points which don't actually fall on a line, what is the best line I can draw if I want to get close to these points and be close to sort of all of them? So what I also want to talk about is how do we actually make these? And what are some different things that we can see when we talk about making them? So I've got to Nope, it's not going. Okay. Oh, was I like an annotator or something? Okay, sorry. There we go. Now I'm allowed to scroll. Okay. So first I want to walk through, oh, and there's a line there still. Sorry, a lot of screens going on. So what I want to talk about is how we actually make these. So let me delete that. So making a chart is pretty easy. Well, I guess easy once you know where to find the buttons you actually have to push. But Excel, if you've, I mean, it is likely you have used a spreadsheet for something or taken a class where you've had to do it, but there's a lot of stuff it can do. And if you're looking for these slightly more advanced things, it's really unclear where to find them if you've never done it before. But in order to make this chart, you first make a table with your inputs and outputs in these two columns. And then you would like to insert a chart. And there are a bunch of different ones. So there's like, we can look at these. A line one. This is, I guess, tracking these values. So I think what this is doing is the blue is these numbers, the first column, the orange is the second column. And these numbers are so big, it looks like this first column is just flat. So that's not what we want. Other kinds of charts, I mean, you can, I don't know what some of these are. It's a sunburst. Okay, I'm not even sure what that is supposed to be. Okay, so there are a lot of different charts. If you want, for a lot of different purposes, we are just looking at the XY scatter plot. So XY like the axes, and scatter meaning like we just threw a bunch of points down. Okay. So a few things that we want to play with here. First is how we change everything is we can go to add chart element up here. So this gives us a lot of different things that we can do. Some of them are more just visual, meaning we can put in the title. And if you click on this, you can kind of change the way the text looks. You can also change what the title is. We can put on some data labels. So let's add in what these numbers are, which can be kind of nice, especially if they're not exactly on an axis. Oops. But one thing that we especially would like to do is, because our inputs start at 10, and by default, the axis starts at 0, we'd like to start a little bit later. So what we can do is say go to axis or axes and more axis options. Okay. And let's try that again. There we go. So the text options is just the words that you write. The axis options is what we actually want. This is color, different effects, the size, but the options is what we really want here. In particular, we have the bounds for the input axis. So this says we start at 0, we go up to 16. Let's start at 10. Click enter, and it remakes it. So now all of our stuff isn't packed into one corner, it's spread out, and so the whole graph is the information that we're looking at. So there's a lot of other stuff that you can do if you cared to make your table all fancy, but this is good enough for us. So what we also want to do is if we add this chart element, there's a trend line, which the picture should indicate you have a bunch of dots and then a line going through it. So we can pick a line and it makes the line for us. In the first example we saw in the slides though, we had not just the line, but we had the equation and this r squared value. And let me make this a little bit bigger. So ways to get there, sometimes if you can click on the line here, you can make it work, but also we can go to more trend line options. So in here, these two are like color and effects. We are more interested in what the trend line actually looks like. So there are a couple options for what the formula of your line is. We'll play with this a little bit later. But what we can also do is display the equation and display the r squared value. You can also make this a little bit bigger. Let's make it like 15. So this is what we had before. Right, so clicking on the line gets me back to the format trend line. Some of these other things here, set intercept, is you can decide what the y-intercept is, besides just adding a data point. You can also forecast, which means this line really just goes over where we have data. But if we say, let's go forward 2 periods, it extends it 2 units. So let's, sure, leave it there. Any questions about making this? Okay. So there's a lot of math that's going on under the hood, which is interesting to people who find it that sort of thing interesting. But also, this is a little more realistic in how this stuff gets used. In order to do this, it's good to have an idea of slope and intercept and how lines work, but actually doing the algebra, a computer can do that. And so let's have the computer do it. So as a comparison, if we take this and this 623, if we change that, either just for the sake of an exercise, or maybe this underlier you investigated a little bit more and realized you forgot to count one of the fields of trees, and so you were just way off. So here we changed that 13,623 to 13,700. So if we go through the same process, so highlight our information, we want to, so you could insert something here. I would say at the top, insert a chart that gives you all the options. We want an XY plot. Make it a little bigger. We want to make the same moves. So the two things we really did were the axes. We want to start later so we don't have all this empty space. And that was in the bounds. We don't want to start at 0. We want to start at 10. We also want to add in well, the other thing we did was data labels. These were kind of nice. Let's put in these below so we have the actual numbers there. And then we want to add in a line. There's a linear option, but because we want the equation and this r squared, we'll go into the full options page. And then we'll shift control click on this or right click, whichever one does give you the options. Let's make this a little bigger. So we can in the same process make this line. And what we can notice is that the r squared has responded. This line, because we have a different data set where we took the point that was really low and we moved it up. This r squared is 0.99, whereas this r squared was 0.909. So as I said, this r squared is how well does your model fit the data. And in this case, it fits much better. And so we actually get a higher r squared. If you have data points which actually are on exactly a line. So you can make this in the same way. But this time, if these 4 data points are exactly on a line. So if you start here and you go up 75, you get 11,675. Another 75 gets you here. Another 75 gets you here. Another 75 gets you here. So if they're actually on a line, this is that specific example we talked about, or we did a few times before, and I've been sort of recycling for a few days now. This line is 75 to x minus 250, and that is the line that goes through these points. And in this case, r squared is 1, and if r squared is 1, that means the line or curve or model you have goes through exactly your points. So one way of using a computer to do the work that we want is you could say, if you had a question, was a line going through, I don't know, -2, 10, and 5, 4. So this is a question you could have. Well, a way you can do this is say, let's enter these as a table. So let's say -2 gets paired with 10, and 5 gets paired with 4. These are our inputs and their corresponding outputs. Let's use these to make a chart, the XY scatter plot. Now we just have 2 points, but we can say between these points, let's figure out the line that goes through them. And here I right-clicked to get some options. We can format the trend line. Let's zoom over here. And let's figure out what this equation is. Let's make it bigger. So what we get is the exact equation of the line that goes through these 2 points. So as a way of, so the work that we've been doing is, I think, it can be done by a computer, but what is, I mean, a lot of mathematical computation stuff, solving equations, finding equations of functions and things like that. Computers can do them, but it's important to have kind of a theoretical background understanding at least a little bit, so you can interpret this and have an idea of what the, or look at this and not be intimidated by it, but also know that how these numbers can be interpreted. So this 4.833, that's the intercept, and that is about right where we cross the y-axis. This is our slope, negative 0.0833, and these are rounded. You could figure out what fractions they are. If you found or if you did it by hand. But this negative number says, so that's the slope, and our graph is going down. So that is what it looks like if your slope is negative, and it's fairly small, so our line is fairly flat. Big numbers here, either big positive or negative, give you really steep lines. Things that are close to 0 give you pretty flat lines. So while in this case we didn't do the work of coming up with this, we didn't use the slope formula and put it in point slope and then simplify, we have talked about lines and their equations enough to look at this and have an understanding of what we should think of when we see these numbers here, how they can be interpreted, and what they correspond to as far as the graph. Okay, but let me jump back here. A kind of surprising picture, which I think is actually sort of cool, is we've been talking a lot about lines. Those are the most basic type of function, and linear models are a good place to start. In a lot of cases, they fit really well. But that is just one type of function, and there are other types of functions and other types of considerations in thinking about how you want to find a model for some data. So in particular, a line might not be the best way to model your data. And what this picture is representing is these are 4 very different looking data points, but they all have exactly the same trend line for them. So this is a drawback, apparently, of trying to use a linear model, in that these really different cases all end up with the same model, and some of them are clearly, well, some of them are clearly not lines, but they're so different, you would think surely the best way to model them isn't with the same line in every case. So in some of these cases, you might say, yeah, this is clearly a curve. We want to find some curved function to try to follow this track. We don't want to try to model it with a line. In this first case, this is where you can try to find functions to fit this, but a lot of it comes down to what do you think is happening? So in this case, if you tried to draw a line that went through exactly these points, you'd have this crazy thing going up and down all over. But a sort of practical need is you'd say, well, in these cases, there's a lot of variability, but there's also a really clear trend. So maybe you don't want to keep track of exactly these tiny fluctuations, but you can say this bunch of dots is clearly going up. And while there's a range of them, nothing is really far away. So they're kind of, if you take this line, they go to one side or the other side, but they don't go too far to either side. They're kind of staying within a reasonable distance of this line. So in this case, you might say this line is off by a bunch on a lot of these, but if you're looking for maybe large scale data, or you want something, you don't want to take into account all the noise, all the little variations that there actually are, a line does a pretty good job. In this case, what you might, or one way of, or a situation where this might be what your data looks like, is a little bit like the tree case. You have things being pretty linear, but then one year there's an outlier. This could, I mean, as an example, be something like the profit of a toilet paper company, to use that example again. Profit goes up pretty regularly every year, but then during 2020, your profits are just through the roof. But then the next year, they're back in line with what you'd expect. So if that's what's happening, you really sort of balance, what do you want your model to do? You have these data points, but if you're trying to predict what happens in this next point, so if you're trying to predict what's happening, you could pretty reasonably say, this is an outlier and we cannot expect that to happen again. So so this line is going up because it's trying to not be too bad in how far it is from this line. But you might also say, well, forget that. That is an outlier. That's never going to happen again. Let's just assume that this line keeps happening. So here, even in this case, these are two lines, which you can use as models. This one is a worse approximation for this data point, but you might have reasons for saying, I want to ignore this one. And given the situation I described with a toilet paper in 2020 is kind of an exceptional year, or like the number of people using Zoom um, or telecommuting. It's increasing pretty normally, huge 1 year, but then it's back in line with your previous expectations. You might have reasons for saying, I'm just going to ignore this data point. That is a little bit of a dangerous thing to do, though, because it might be that these outliers, if there are more outliers in quotes to come, this isn't really an outlier. It's just ahead of the curve a little bit. You just haven't seen that this is the new normal. So ignoring outliers because it doesn't fit what's happening is something where there's some risk involved. You have to make a decision. Do you want to use this point, or do you have enough justification to say that this isn't really the point that I want? I have reasons for thinking this point is not representative of what's going to happen in the future. And this is another weird set of points which gives you the same line. So lines might not be the best way of fitting data. They're nice because they give you a very simple equation, and sometimes simplicity has a lot of value on its own. But to see that sometimes we want better or other functions to give us other, or to model data better, if we say, we don't need, sure, we can make this years and trees, but we don't really care about that. So if we have these data points and we plot them, I want to label this data. Okay, chart design, that gives me these. So let me put in the labels below again. Okay. So here for data points, and the line does a pretty good job. We can get the formula for it, and R squared is 0.98, which is pretty good. It's pretty close to 1. But what you might notice is that if you took, or this line, these data points here, they're getting, so we're above it and then we're below it, so they're kind of curving up. And so having a different looking function, these are the same data points in these next few examples. So what we did here, we format trend line. We went with a polynomial. A polynomial is this kind of function where it has powers of x. So here we have x squared and x, and we have these constants multiplied and added to those powers of x. So a polynomial is anything that looks like that. The order is how big of a power do you want? So if we give ourselves an extra term here that says has an x squared, it looks like this data fits much better if you're allowing it to curve. And you maybe didn't really think about it when you had this line, but comparing these two, you're like, oh, wow, it really is pretty curved. That's what it should look like. And you can keep changing this power. So it turns out if you give yourself a third power, you can get exactly these points back. And in general, here we're kind of lucky, but in general, if you have, no, this is right. So in general, if you have some number of points, you can fit them perfectly with a polynomial with the power 1 fewer than the number of points you have. So that means if you have a line with if you have 2 points, you can fit them with a line which just has a first power. If you have 3 points, you can fit them with a order 2 polynomial, so a square. And if you have 4 points, you can fit them with 3, and so on. So actually, if we have this problem, if we want to find a parabola, this is the shape that the x squared polynomial has. Going through 2, 2, 1, 0, and 5, 9. So because we have 3 points, we can fit them exactly if we give ourselves an x squared term, and if we give ourselves a power of 2. So again, we make 1, 0, 2, 2, 5, 9. Make ourselves a little chart. Let's add ourselves a trend line. We want to pick what type we want it to be. We'll make a polynomial of order 2. Let's check this, and as expected, we have this r squared of 1, which means we fit it exactly. So to fit 3 points, you can do it exactly if you give yourself a square. In this point, if you have 4 points, you can fit it exactly if you give yourself a third power, and this pattern keeps going. So giving yourself more terms, higher powers, gives you more kind of flexibility or curving in your function, which can let you fit the data better. The trade-off, I guess, is this is a much messier looking function than a line, for instance. So maybe if you just want something that's pretty good and easy to understand, a line is better. If you want to fit it exactly, you can have this polynomial. There's also, in this case, this trend line, which is called exponential. So E here is a number. This is like, E is 2.71828 and so on. So E is some number that appears in calculus. And if you take this number, almost 400, times E raised to this decimal times X, that gives you this equation here. So there's other exponential looking functions, which is kind of the topic we're going to talk about next, which fits this even better, 0.996 of an r squared. And in this case, if we drop it down, we have 0.993. Okay. So, okay, we have a last example I kind of want to talk. No, I'll do this next time. Okay. Um, so using technology, we can find, given data points, there are a lot of different functions that go into them. So it's not just find a line that fits all these points. It's really, do I have a reason for thinking a model should look like this, and how well does that fit? So given just a couple of points, there's a lot of flexibility as far as what function can reproduce those models. So we'll be talking I'll do a couple more examples, a few things I want to show you guys, but then we're going to talk about a different type of model, exponential functions, that E showing up, which is where instead of taking a number and raising to a power, you fix a number and start raising it to different powers. So those give us different kinds of functions. Right, so next time we'll look at some more graphs and talk about what different models can look like. And until then, there's a homework due. Make sure you do that. Catch up any old homeworks if you ever missed one, including the Piedmont Symposium summaries. Those are still online, so take a look at those. Other than that, I can stick around if you have any questions. And oh yeah, and also email me if you want to talk about a potential project. But other than that, have a good weekend, and I'll see you guys on Monday.